Okay, good morning. I'm Mike from Princeton University, and I'll be presenting TigerCub, which is Princeton's first PocketQube platform. But to start, I wanted to say, like, as part of the American contingent here, I haven't been watching the American news this week, but whatever we may or may not have done this week, I'm sorry, and we definitely won't do it again. So I'm part of the Mechanical and Aerospace Engineering Department, just in hopes of getting some of you to chat me up at the networking dinner tonight. I'll talk myself up a bit. My background was Lockheed Martin Space Systems. I came to Princeton as part of our exoplanet telescope research group. We pretty much invented direct imaging of exoplanets. I did that for a few years, and then the last few years I've been part of our space physics group, which works on heliophysics and solar wind missions. In particular, we're working on the IMAT mission right now, which you can see some photos of in the bottom here. And that's supposed to launch towards the end of this year, and I think we're on track for that. But also, aside from my research, Princeton lets me do some teaching and mentoring, so I'm instructional staff for our space systems design class, and I'm the PI for our TigerSat's student nanosatellite group, which is actually my favorite part of my job, so I'm just trying to keep growing that and less bureaucracy. But I have to do 2 bio slides because I'm actually not presenting any of my own work here. All of the work in this presentation is from one of my fantastic undergrad students last year, Candace Doe here. She was a senior last year, and she designed an entire PocketQube as her senior thesis. It won the best overall thesis in our whole department. She was accepted to present it at SmallSat 2024. She's now a grad student in Georgia Tech's fantastic graduate CubeSat lab, and she's interned at Firefly, Rocket Lab, and SpaceX Starlink. So she couldn't make it today, but I'm sure she would love it if anybody here wants to connect with her on LinkedIn. So yeah, Candace. So first, the layout. I want to use the layout as an excuse to stress throughout that TigerCub, we designed it as a mission agnostic platform, so it does not have a payload. It has just volume and budgets allocated for some future TBD payload, because as a mechanical engineering department, we were more interested in the challenge of designing a vehicle, and we'll figure out the payload later. So you can see the layout here. I would say the main motivation for this layout and this platform is an excuse to integrate an Iridium radio as the primary comm system, in particular an off-the-shelf Iridium unit called RockBlock. You can see the RockBlock here, and I'll talk a little bit more about why we're so interested in Iridium as the comm system. But you can see the rest of the layout here, and I'll be going through it board by board in the stack. So yeah, the RockBlock, it's off the shelf, it's cheap, about $300, and we just discovered it happens to be a perfect size for a 1P PocketQube. So motivation is, I feel like the elephant in the room is, even today in 2025, almost half of educational nanosatellites arrive dead on arrival to orbit, meaning they don't downlink a single packet, and that's sad after many years of work. And we in particular, as a mechanical group, we're all undergrads. We have no grad students, and we don't have any RF engineers. We don't have any electrical engineers. We don't have any software engineers. So we were looking for how we could most easily risk retire our link budget, and Iridium's kind of a cheat code for that, because it works better in space than it does on the ground. On the ground, you're beaming your packets up to Iridium's own orbiting satellite network, and you have to penetrate cloud cover and atmospheric losses just to get to the orbiting constellation, and then they downlink your packet back to Earth to their own cloud platform. So if you can prove that you're downlinking packets from the Earth, your link budget actually gets better in space. So it's an easy way to risk retire your link budget. We could also shortcut our ground station because we get to use Iridium's cloud-based ground station to view all of our packets. So we are working on a ground station, but for this mission we could skip it and just use Iridium's. And then a nice bonus of Iridium is you get full orbit coverage, so you can downlink almost through your entire orbit rather than having to wait for overpasses. And so as first-time PocketQube developers, we actually have a ton of questions for you guys. So for the Iridium, I'm interested if anybody else here has any flight heritage flying an Iridium radio or a rock block unit. We found this 𝗖់{VERY} mission back in 2022, flew an Iridium modem, but they had a deployment failure, and so they couldn't prove it out on orbit because I think they were blocking their antenna by accident. We also noticed the rock block in particular has these electrolytic supercapacitors on it that charge up and they're responsible for powering transmission. I know electrolytic capacitors are kind of sketchy in orbit, so we did find a paper, an 𝗖cie paper here, suggesting that these particular supercaps are flight qualified, but we're interested in if anybody's had any unfortunate surprises with electrolytic capacitors in orbit. And then FCC licensing, if anybody's tried to fly an Iridium radio, I'm interested if you've heard, if you've received any pushback on trying to license your radio. So you can see the rock block is suspended above the rest of our stack here, and the rest of our stack is we tried to do a standard PQ9 format, but the rock block is larger. So that was a nice excuse to mechanically suspend it above the rest of the stack. So we got to design this cool bent sheet metal frame. So one of the focuses of my group is we try to design rapid prototypable parts for all of our nanosatellites. And by rapid prototypable, I don't always mean 3D printable, although we design a lot of 3D printable parts. But by rapid prototypable, I mean we design a file that can be uploaded to any rapid machining vendor in the world, often get an immediate quote, and be able to get the part as is, as we designed it, in our mailbox, in a few weeks. And Candace succeeded at this here. She designed this sheet metal design that we can just send this 3D file to any sheet metal vendor. We'll get it back precision laser cut and precision bent with all the bends already done so that we don't have to do any in-house machining or any in-house bending. That work can be enriching, but for your schedule-constrained projects, it's nice to be able to just outsource a lot of the mechanical parts. And then even you get these nice little bent tabs for mounting the solar panels on the outside, and those came out nice as well. So the solar panels, we chose these 𝗖cie cells, and I think we've been seeing a lot of these here in the presentations. My lab has done a lot of groundwork on comparative testing of the monocrystalline silicon cells, like the 𝗖cie cells, and real space-grade triple junction cells. And the triple junction cells are specified to have much better performance, but by the time you integrate it into a panel and start tumbling it, in our lab with a solar simulator, we just could not convince ourselves that the triple junction cells were worth the extra cost and the extra complexity of integration. So we're really happy with the monocrystalline silicon cells. And those, contrastingly, are $8 each on DigiKey. We did an optimization to find the max fittable power collection using 𝗖cie cells on a PocketQube side panel, and that's how we settled on this part number, which if you can fit 2 of them and get a maximum 370 milliwatts per 1P panel. Now that's a best case, after assembly and especially with tumbling losses, you don't get anywhere near 370 milliwatts, but that's the max possible with one panel. So anyway, for these cheapo cells, we're interested in anybody have flight heritage with them, and they don't have cover glass, unlike usual space-grade triple junction cells. So we're interested in if anybody has found any thermal surprises or seen any significant radiation degradation, in particular for groups that have achieved pretty long missions. Have you seen any surprises from these cheapo cells? I see some nodding here. Please come talk to me. And then lastly, In particular, for any groups that have tried to get approvals through in the US especially, this is a tiny 1P with body-mounted panels. Has anybody, run into obstacles with the radar cross-section problem? I mean, this is a tiny radar cross-section. We don't have deployable panels. We don't have deployable anything. So please tell me if you've hit roadblocks with the radar cross-section requirement, especially for US approvals. Next on the top of our stack is our EPS. So Candace, again, we're mechanical engineers. Candace did not feel qualified to design a flight-ready EPS herself, especially in the tiny fraction of her one-year project. So she found this open source EPS from a PocketQube kit called OpenSource DynaSat kit. And it has a lot of bells and whistles. It has maximum power point tracking. It has battery charge monitoring. It has a few different voltage regulators. So it's got a lot of nice features. But we're interested if anybody, the kit seems to be defunct. We haven't been able to find any contacts for it. So we're interested if anybody has any flight heritage with this kit. We can't find, it has its own microcontroller for controlling the EPS itself. We can't find the stock firmware for that microcontroller, and we don't feel like writing it ourselves. So if anybody has the firmware for this unit, please tell me. And then our battery, right now we just have a cheap battery it's cheap lithium-ion battery from Amazon. DynaSat recommends a particular part number. We used a slightly smaller part number in this 35 by 25 by 7 millimeter size, where we could get 600 milliamp hours. But we're just interested if anybody has flight heritage on a battery that small, that we could use instead of a cheap Amazon battery. And that's in particular because Candace did a transient thermal analysis on our mission, and she found, I mentioned yesterday, she found that we look pretty happy thermally in a sun-sync orbit, but as soon as we get any sort of extended eclipse, our battery's in trouble because we're way down in the -30, -40 C range during eclipse. So next is the onboard computer, data storage, and attitude determination. This is a two-board stack because we had to spread it across two boards just to fit it. We just use a Teensy, which is a tiny version of Arduino. We just try to come up with ultra-low data rate missions that we can run on an Arduino. So we don't even have an operating system. We're just running a scripted loop on Arduino. And we do have watchdog timers, so the satellite will reset itself every time the Arduino loop freezes, but otherwise our flight software is super simple. So that's one of the boards, and then on the top board we fit a micro SD breakout board and the smallest 9 degree of freedom IMU that we could find. So lastly, Candace was really interested in her thesis report, including a payload user's guide, like an actual professional user's guide. So if anybody's ever read a launch vehicle user's guide, she was trying to mirror that approach. And so in her thesis, she has this whole chapter where she outlines all the accommodations for the payload, namely volume, footprint, power, data budget, thermal, structural, because the payload is the bottommost board in the stack, and we have allocated budgets for it. It's probably a single board, but we do have a cutout available in the base plate. So your bottom board payload can either look to get space viewing through that cutout, or if you have a large payload, you can even extend downward, maybe a tiny telescope. You could extend downward into that window. And then all of this is open sourced on Candace's GitHub. I don't have a fancy QR code, so I'll just leave this up here for a second in case anybody wants to take a photo, but everything's open sourced. Her whole thesis is open sourced. You can see this is the form factor for the boards. We tried to follow the PQ9 footprint, except for our connector, we found we needed 10 pins, so she just made a PQ10 variant of the connector. So I'll leave that up here, but next steps for us, we have signed a contract with Alba for an upcoming launch, 1P launch that we're excited to announce here today. We don't have a mission, we don't have a payload, we need ideas, but for the fall semester, I'm going to hand Candace's design off to our larger rocketry club and say, here's a vehicle, you design a mission, you design a payload, and let's get down to the business of really qualifying this for launch, including licensing, collision avoidance, deorbit, and especially my lab is really interested in doing our own qualification testing. So we have a thermal cycling chamber, we have a tiny little shaker, and we're excited to qualify this platform ourselves. So lastly, hopefully I have some time for questions, or I've listed all the questions I've asked here. So if you have answers to any of my questions, please raise your hand and holler, or come grab me at one of the networking sessions and answer my questions. And the most important question, does anybody else want to fly this platform, because it's all open sourced? Okay, questions? Do we have time?